All right, now let's start to look at similar triangles. We've been talking about triangle congruency this whole time, this whole review, and now we're going to look at this new concept called similarity. So let's go ahead and fill in the blanks here. Use the questions below to keep track of key concepts. Practicing, let's summarize, filling in the blanks. Okay, so similar triangles are triangles that have the same shape. Congruent triangles have the same shape and size. So completing the Venn diagram here and the sentences below, write congruent or similar in each blank. So triangles that are similar have the same shape, and then some triangles have congruency, but so all triangles are similar and some triangles are congruent that have the same shape. All congruent triangles are similar. Only some similar triangles are congruent. Okay? All congruent triangles are similar. Only some similar triangles are congruent. All right, let's go to the next page here. Your own words explains what it means to dilate a triangle. To change a triangle's size without changing its shape. Okay, let's make a mental vision of this, mental image. So here is my original triangle. Can you imagine if we shrunk it? Taking this AB and just making it smaller. Taking this AC and making it smaller. It's like making a little tiny baby version of the original. And then if this was my original and we're talking about an enlarged one, picture this AC gets doubled in length, picture AB gets doubled in length, and picture that BC gets doubled in length. I don't know, something like this. I'm even going outside the box. Okay, so these are similar triangles. It's like a mama, a bigger triangle that's been enlarged, and a baby version of the original. They are still the same shape, but they are not the same size. Dilation similarity rule. If you can dilate a triangle A so that it is congruent to the triangle B, then the originals are similar. So if I can take this triangle and stretch it out to be this exact one, congruent, or if I can take this one and shrink it down to be this exact one, congruent, then they are similar. Now, way down here at the bottom, triangle ABC is similar to triangle DEF. That's going to go with the next page here. These little lines, see these lines at the top? So I'm going to go back down to that original page, and I'm just going to write it here. I don't want those blank lines away from it. But so what is the notation we would use to write this? We would write triangle ABC is similar to triangle DEF. So this new symbol right here is our similarity symbol. So think about the congruency symbol, how it has an equal sign with the tilde on the top. Now this is just the squiggly line without the equal sign underneath. So this means similar. Okay. All right, let's say Organizing this info and drawing inferences, use the two similar triangles on page 12 to fill in the tables below. Then use the table to infer a rule. So corresponding angles, triangle ABC, if angle A is 39 degrees and angle B is 54 degrees and angle C is 87 degrees, and we know that these two triangles are similar, then we know that their three angles are the same. So the corresponding angle, angle D, is also 39. The corresponding angle, so look at middle position is they're both 54. And 87 for angle C, last position angle F, sorry, not 84, 87. And so we are going to notice that each pair of corresponding angles is congruent. And similar triangles have congruent corresponding angles. That's the rule. Okay, let's go down here to this next section, see what this says. All right, corresponding sides. What if we measured them? Let's say, for example, that side AB was a measure of 16 units, side BC was a measure of 20 units, and side CA was a measure of 12 units. And then we noticed as we measured the other three that this one measured 8, this one measured 10, this one measured 6. What we would notice is there was a ratio from triangle ABC to DEF, and that is that 16 is to 8, or 2 to 1. 20 is to 10. Sorry, guys, this one right here has a typo. Or 2 to 1, and 12 to 6, or 2 to 1. There is a 2 to 1 ratio. So the lengths of corresponding sides in similar triangles are or have, oh, sorry, I was writing the wrong word, equal ratios. They are proportional. Similar triangles the lengths of corresponding sides to similar triangles are proportional. And so right here, similar triangles have proportional corresponding sides. It looks like this has changed since our book last year. So proportional corresponding sides. Okay, so did you notice that these were 2 to 1? So it's like we're going to be saying things like certain triangles are half the size of the original. They are double the size of the original. They are triple the size of the original. There's going to be a proportional relationship. Okay, let's look at this next one. All right, corresponding angles. So this is now the official properties. Corresponding angles are congruent. Corresponding, side lengths are proportional. So the scale factor is the key word that we're going to be using here in our dilation conversations and in our triangle similarity conversations. The equal blank of corresponding side lengths. Actually, let's call it a ratio. The equal ratio of corresponding side lengths in similar triangles is your scale factor. So this is a definition that we want to remember, that the scale factor is going to be how much your triangle grew. So how much did the triangle shrink or grow? And that's going to be your scale factor. All right, identify. So now we have our steps, how to calculate the scale factor. Identify the corresponding parts, corresponding sides. Write each pair of corresponding sides as a ratio fraction. Substitute the side lengths for the side names. and then simplify the fractions. So what do we mean simplify? Like back here on this other page, we got a 16:8 ratio. So then we simplified that to 2:1. It would be like if you had 16/8, it becomes 2/1 or 2. All right, for a triangle A similar to triangle B, if A is bigger than B, the scale factor is less than 1. If A is bigger than B, the scale factor is less than 1. If A is smaller than B, the scale factor is greater than 1. Okay, if triangles... Ofe, estoy haciendo un video. Está bien. The triangles in below inside AB corresponds to side DE. Are the triangles similar? So now we're getting an actual practice of two similar triangles. So we're going to test out some things here with side lengths to see if they're similar. So step 1 is to identify the pair of corresponding sides. So looking first at side AB, do you see that that would match up here to the DE? And side BC, right here along the diagonal, would be with EF. And CA would be with FD. I hope you're getting good at these corresponding parts. Find the scale factor for each pair of sides and simplify the fraction. So AB over DE, we go up and find that AB is a side length of 7 and that DE has a side length of 29. We notice that BC has a side length of 24 and that EF has a side length of 96. And finally, 25 to 100. But notice that these fractions are not simplified. What can go in? Well, first of all, can anything go into 7 and 29? No. So notice there's not an equals. It's already simplified. But with 24 and 96, I know at least a 4 can go in. Let's test what else might be able to go in. 96 divided by 6. Okay, 6. Okay. Let's see if 24 goes into 96. And it does. Okay, so 24 goes into 24 once. 24 goes into 96 4 times. So see how that works out? So this is a 1 to 4 ratio. Finally, 25 goes into 25 once. 25 goes to 104 times. It's a 1 to 4 ratio. Okay, so what does this mean, what we found? The ratios are not equal. Even though this one and this one are equal, this side length is not. So the corresponding sides are not proportional. It has to be all three. So the triangles are not similar. So what we just performed was a test on these triangles. We just did a test to see, do I have 3 proportional sides? And if I do, if the ratios match, then they're similar. But I don't. This first one threw it off. So they are not similar.